Well, hello and welcome to some further review in optimization. I have two problems from the textbook chosen that I think are further problems that will help you to see the ways in which optimization can be used in a wide variety of settings. So these are a little bit more difficult problems. They're a little bit farther off of sort of the beaten path that you may be used to seeing, but they provide a good review of some of the problem-solving skills and techniques you can use in solving these problems. Okay, our first problem has to do with geometry and distance on the coordinate plane. This is problem 41 out of the textbook, page 229, so you can read the original problem there. And the question we have here is, how close does the curve y equals the square root of x come to the point 3/2, 0? And this is a problem that it is very good to have a picture of, because it's not obvious necessarily right off the bat what we are asked to think about here. So here we have the coordinate plane, and let's just do a rough sketch here of y equals the square root of x. So here's our function y equals the square root of x, and we have this point 3/2, 0, and let's suppose that point is somewhere like right here. So here's our point 3/2, 0. You'll notice that we can take this point and we can think about connecting it up to different points on this graph. And every single one of those lines, every single one of those dashed lines has some distance. There's some distance between this point and the curve y equals the square root of x. What we're asked for in this problem is to basically figure out what the x and y coordinates are of the point that is closest to the point 3/2, 0. So we're trying to find the shortest distance between this point and this curve. That can be a little bit challenging. We can think about what the distance formula looks like. Recall from your geometry days that the distance formula, the distance between 2 points, is given by the square root of x1 minus x2 squared, the difference in x coordinates between the 2 points squared, plus y1 minus y2 squared, the difference between the y coordinates squared. And this is really just the Pythagorean theorem in another guise, right? We use this the same way we would use the Pythagorean theorem. This is a very ugly equation, right? The distance here being a square root function of a square root function, we're going to have a lot going on here. One of the hints they give in the textbook, and one of the things you should realize here, is that if the distance is as small as possible, then so is the square of the distance. So rather than do this problem with the distance formula as written, I'm going to look at the square of the distance, which will be a much easier problem to look at. So we have x1 minus x2 squared plus y1 minus y2 squared. Now if I minimize the square distance, that's also going to solve this same problem, because if the distance is the smallest, then the square of the distance will be smallest also. So how does this fit into our problem, and where are the pieces that we look for, right? If you recall from the original discussion we had, the original lecture we had on this material, we had two different purposes here. One of them was to determine the function that we're trying to maximize. In this particular case, our function that we're trying to maximize is this distance formula. And what is our constraint? What is the restriction we have on our values? Well, in here we kind of have two things you might consider constraints. First of all, we know one of the points has to be this point, this 3/2, 0. And the other constraint is that when we go to find points on the curve, they have to be points that are on the curve. They have to be points where the x and y coordinates satisfy this relation. So we're going to combine these three things together to come up with a function, and we're going to then find the maximum, or in this case I guess the minimum value, the extreme value of this function. So let's go ahead and take a look at what this looks like. I'm going to go ahead and call this x1 and y1. These will be our original points. Then x2 is something that we have freedom to choose, right? We can choose any x value on the curve here. What's going to happen is the y value will be restricted to the y values that we have here. So we're going to call our y2 the square root of x. That's the relationship, that's the constraint that our function has to solve. Remember, we need to somehow get rid of a variable, and in the distance formula we have two variables. So let's go ahead and do this. The square of the distance in this particular problem will be 3/2 minus x squared plus 0. 0 is the y coordinate of our point 3/2 comma 0 minus the square root of x squared. And that square root of x is the constraint, right? The y coordinate for the point on the curve has to satisfy that connection. It has to be the square root of the x coordinate. So this is our function. This is our function that we want to minimize now. And so we'll go ahead and do this. And I'm going to just find the derivative of this function. So I'm going to take the derivative of this 3/2 minus x squared plus 0 minus the square root of x squared. And maybe it's going to be useful for us to do a little bit of simplifying here first. We can rewrite this as the derivative of 3/2 minus x squared plus, and now notice that the 0 minus x is really negative square root of x. When we square that, we just get a plus x here. So this is the function that we're going to take the derivative of. This is a much easier function to work with. Recall, if we would have used the original distance formula, we would have had a square root of this entire thing, which would just make it a more difficult problem to work with. We would still get the same answer. So now we can go ahead and find the derivatives here. The derivative of this first term, the 3/2 minus x squared, we need to use the chain rule. We bring down a 2. So we have 2 times the 3/2 minus x to the first power, but then we have to remember to take the derivative of what's inside the square. That's the 3/2 minus x. The derivative of that is minus 1. And then we have the derivative of the second piece, the derivative of x, which is just 1. In order for this to be a minimum or maximum, we have to set this equal to 0. And what this will do is this will find the x-coordinate on that curve that has the smallest distance. Now, how do I know I'm going to get a minimum here and not a maximum? That's always a question you need to ask yourself, particularly when you're dealing with polynomial functions where it's possible to have maximums or minimums. If you look at the original problem up here and we look at the graph, okay, if we look at the relationship that we have here, notice that while I can make a small distance by choosing a close point, I could make the distance as large as I want to be by simply choosing a point that's very far away, a very large x value for the function. That would give me a point that was very, very far away. In fact, I could make that distance as large as I wanted. So this particular problem has no maximum value. There's only going to be a minimum value, and that's what we're looking for here. So let's come through and solve this now. First, let me distribute the 2 and the minus 1. That's going to give me a minus 3 plus 2x plus 1 is equal to 0. Or minus 2 plus 2x is equal to 0. 2x must equal 2 then, and that tells me that x equals 1. Remember that I'm asked to find the point where these two curves come closest, where this curve and the point are closest, so I must also find the y value. But the y value, remember, is just the square root of x. So that simply gives me y is equal to 1. So the answer here, the closest point on this curve to the point 3/2 comma 0 is the point 1, 1. So you may wonder, why did they pick the point 3/2 comma 0 as an evil point to pick? Not really. It gave us a nice clean answer here, this answer 1, 1. Okay. So again, go back through. If you didn't follow all the pieces there, come to class with questions. But this is a good example of a more abstract or algebraic problem that we may be trying to solve with these optimization kind of problems.